Hi guys, let's derive potential energy to an electric dipole which is placed in an electric field, in a uniform electric field. So till now we derived potential energy expression for a single charge, two charge system or multiple charges. We know what is an electric dipole. Suppose electric dipole is a setup. Suppose if we take two oppositely charges, one is negative q, another one is positive q. So this is minus q charge and this is plus q charge. So they are separated at a distance of 2a. So this 2a we call it as dipole length. Now this setup we are calling an electric dipole. This electric dipole having dipole moment. So the dipole moment is always from negative charge to positive charge. We can mention the dipole moment as dipole moment P equal to, it's the magnitude of any charge times dipole length 2a. So dipole moment P equal to 2aq and the direction of the dipole moment equal to negative charge to positive charge. So this is the background knowledge about electric dipole. Now if you place this electric dipole in an electric field, suppose at an angle, so this is the electric dipole which is making an angle theta with the electric field. Now if I mention that two charges at here same, so let me take this as a positive charge and this as negative charge minus q, and the dipole length, so this is dipole length 2a, and the dipole moment directions, it is from the negative charge to positive charge. Now this dipole is present in an electric field. So this electric field apply a force on the both positive charge and negative charge. So if you mention that force it has, since it is positive charge, so this is the force directions along this direction, and if it is, let me take this force, if you can mention force F equal to the relation between charge and electric field positive QE, it's a positive value. Similarly for the negative charge, so it is in this opposite directions, so that force F equal to minus QE, and we define a torque tau equal to, or tau equal to force times perpendicular distance. So if I draw a perpendicular along in this direction, so this is my perpendicular, and if I can take base also at here from here to here, so this perpendicular distance, so this equal to 2a sine theta. So that we can get it by considering as this AOB triangle. From triangle AOB, AB value equal to 2a, we need to get OB. OB equal to how much? You can write sin theta equal to perpendicular by hypotenuse. Here the perpendicular equal to OB and hypotenuse equal to 2a. Therefore OB equal to 2a sin theta. So that OB only we are calling perpendicular distance. Now for a dipole, we can define tau equal to, here the force, Coulomb force, you can take any magnitude, QE times 2a sin theta. So we can write that as 2QE sin theta, or we can mention that in terms of 2QA. Here we need to write A, Now tau equal to 2qa e sin theta. Now 2qa you can write as dipole moment, tau equal to pe sin theta. So this is the expression for torque of an electric dipole. What could be the cause for this torque? The torque causes due to because of these two opposite forces. So these two forces oppositely they are acting, so they forms a couple. So couple means nothing but two equal and opposite forces acts at a point. So because of that couple, so torque will be acts on the dipole. Suppose if you take it here, if the dipole is rotated a small angle d theta against the torque acting on it, then the work done is, suppose if the dipole is rotated against the torque, at an angle small theta, at an angle d theta, then the work done is, so we remember the work formula, work equal to force times displacement. So this is the work formula. The same work formula follows everywhere, but here, so it will be changing. Here the force is nothing but torque is force times the displacement. Displacement here it is the small displacement d theta. Now to rotate a small angle d theta, so we need to do a small work dw. Now dw equal to, you can substitute the formula tau equal to pe sin theta d theta. To calculate the total work, to rotate from theta 1 to theta 2 at two different angles, so we can do the integration. So w equal to integral theta 1 to theta 2 dw, which equal to integral theta 1 to theta 2 pe sin theta d theta. Now you can write the work done. So pe is non-integrable terms, so you can write out of integration theta 1 to theta 2 sin theta d theta. Do the integration for sin theta, we can get that w equal to pe sin theta integration minus cos theta, so theta 1 to theta 2. So final expression is w equal to pe, you can substitute the limit, minus cos theta 2 minus of minus cos theta 1. So if we can multiply inside the minus, w equal to pe of cos theta 1 minus cos theta 2. So here theta 1 and theta 2 are the, theta 1 is initial angle before work done, to rotate an angle theta 2. So this is the work done formula we can get for an electric dipole in an electric field. So we know that this work done is stored as a potential energy U of the dipole. So if we can write that as, so this work done is stored as the potential energy. as the potential energy U of the dipole. Therefore, we can write that U equal to P of cos theta 1 minus cos theta 2. So this is the final expression for the potential energy for an electric dipole in an electric field. Now, for the better understanding, let us take a case. That case is initially the electric dipole initially making at an angle of 90 degree. Suppose if we take an electric dipole at an angle of 90 degree, so initially it is making an angle of 90 degree. So let me draw an electric dipole. So let this electric dipole initially is making an angle of the 90 degrees with the electric field. So let this is the negative charge and here it is the positive charge. And this is the dipole length 2a. Okay. From theta 1 equal to 90 degrees to rotate theta 2 at an angle of theta. So I want to rotate from 90 degrees to at an angle. So let me take as an arbitrary angle. So I want to rotate that 90 degrees to at an angle theta. So this is the minus q and this is the plus q. So what could be the work we need to do? So in that case you can substitute the potential energy formula. Potential energy equal to U equal to P cos theta 1 minus cos theta 2. Now substitute the corresponding theta 1 values. You can get potential energy U equal to P of cos 90 degree minus cos theta, because another angle we need to make it turn to another angle of theta. Now if you can get cos 90 value goes to 0, potential energy U equal to minus Pe cos theta. Now this potential energy is a scalar, so we can write that as negative of P bar dot E bar. The dot product of two vectors. The dot product of two vectors, one is the electric dipole vector, second one is electric field vector. So this is the simple potential energy formula we need to remember. Okay. Now here we can discuss certain cases. So in that certain cases, let us take as a first case. If we can take as in case 1, that case 1 called as position of stable equilibrium. So for the position of stable equilibrium, so that is if theta equal to 0 degree. Now in that case you can substitute U equal to minus Pe cos theta, that implies minus Pe cos 0 degree. Cos 0 degree value will gives the 1 which equal to minus P dot E. So in this case what happens, the potential energy U equal to which is U equal to minus P. It tells about U equal to minus P, that is potential energy of a dipole is minimum when the dipole moment is parallel to electric field vector. So here the theta is angle between P bar and E bar. Theta is angle between P bar and E bar, dipole moment and the electric field. If that angle between them goes to 0 degree, then the potential energy equal to minus P. Now that we can mention as the potential energy of a dipole is minimum when dipole moment is P bar is parallel to electric field vector. Dipole moment vector is parallel to electric field vector. So this is the case for the stable equilibrium. So the dipole do not move, it remains stable. Let us take another case 2. Now I can take as an case 2. So in the case when theta equal to 90 degree, that is dipole moment vector is perpendicular to electric field vector. So in that case potential energy equal to minus P cos 90 degree, which equal to 0. So the potential energy value equal to 0 in this case when the dipole is perpendicular to electric field vector. So we can mention that as potential energy is 0. Now let us take the final case 3, when theta equal to 180 degree. It's a dot product. When theta equal to 180 degrees, that is dipole moment and electric field are anti-parallel. So if the electric field is in this direction, the dipole should be in opposite to the electric field. The dipole moment direction should be opposite to the electric field direction. So by that case, if you can take that potential energy U equal to minus P cos 180 degree. Cos 180 degree value is minus 1. So P of minus 1 which equal to P. So the potential energy is equal to positive. So the potential energy of an electric dipole is having positive value. So here you can take cos 180 degree equal to minus 1. Now here we can mention, here you can see the potential energy is positive. It means that is potential energy of a dipole is maximum when its dipole moment is anti-parallel to electric field, external electric field. So this is unstable equilibrium. This is a position of unstable equilibrium. So the potential energy of an electric dipole changes depends upon the orientation of the dipole moment along with the electric field vector. So if I mention in the diagrammatic form, suppose if this is electric field direction which is purple in color, and dipole moment direction. So if it is electric dipole which is black in color, now this is P bar black and E bar, they both are in the same direction, therefore theta equal to 0 degree. So in this case potential energy equal to negative, so which gives us a stable equilibrium. Now the potential energy value is minimum. Now if you can take another case, the angle between dipole moment and electric field vector. Suppose in the second case, if this is the electric field direction, which is in purple in color, and if I take dipole moment direction, so this is the dipole moment direction p bar. Now the dipole moment is initially making an angle of 90 degree with the electric field vector. So in this case, the potential energy of an electric dipole is 0. So the dipole moment do not move at all. So it's do not having any potential energy. Now final case, if you can take as unstable equilibrium, suppose if we can take that as if electric field vector is purple color, so this is the electric field vector, and if you can take the dipole moment, so the dipole moment is now in this opposite direction, now p bar. Now electric field vector is anti-parallel to p bar vector. Dipole moment is a vector. Now in that case, theta equal to 180 degree. So the potential energy equal to P. It is having maximum potential energy. So it depends upon the orientation of the dipole in an electric field. So its potential energy is depends. So that we will calculate by deriving a simple relation between potential energy and dipole moment and electric field. So this you remember it carefully, that is potential energy U equal to P bar dot E bar, the dot product of dipole moment vector and electric field vector gives the potential energy of an electric dipole in an electric field.